Hello and welcome to today's webcast brought to you by Hach Company. Today's event, Off-the-Shelf Real-Time Control, will be presented by Bob Dabkowski, wastewater specialist at the Hach Company, and the event, of course, is sponsored by the Hach Company. This presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. If you're running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of the live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the homepage at waterworld.com. Our speaker today is Bob Dabkowski, a wastewater specialist with Hach Company. Bob serves on the Water Environment Federation's Automation and Information Technology Committee and is on the rewriting team of WEF's Manual of Practice. In the 14 years he's been with Hach, he has consulted with wastewater plants for process analysis and control and authored several articles and white papers on process control and automation. Bob, take it away.
Thanks, James. Thank you all for attending today. I see a lot of virtual familiar faces in the audience, friends from Veolia, American Water, and other places. I do appreciate you attending today, and I want to start by making two promises right off the bat. The first and foremost promise is I sit on the other side of these presentations often, listening to podcasts, listening to webcasts, and the one thing I recognize is a dynamic speaker makes all the difference. So I'm going to do my best today to be as dynamic as possible and keep your attention through the next 150 slides. Oh wait, only 15 slides. Okay, we pared it down just a little bit for you. And the second promise I want to make today is please ask questions. Use that question box. And if I don't get to your questions by the end of the webcast today, we will answer all those questions either via telephone or via email. So please, if you have a question, type it in there, and we will get back to you on those questions. With that, let's get into it. Today, our topic is on real-time controllers. And for those of you in the audience who may be familiar with automation and control, this is not necessarily a new concept, but the idea of how we're packaging them and how we're implementing them is a new concept. These real-time controllers are, in essence, off-the-shelf products that are designed to plug right into your existing system and literally be operating and controlling a process within a day. What types of processes, you're probably asking? There are three that we're going to cover today. The first is chemical phosphorus removal. The second is nitrification control. That's aeration control based on ammonia. And then lastly is nitrification and denitrification control, which is specific to oxidation ditches or sequencing batch reactors that perform on-off type of aeration. So those are the three modules we're going to cover today and talk about these applications in more detail. So we're going to begin with the phosphorus control system. We call it the P module. Basically, it's designed to automatically control the chemical dose in real time based on the load of phosphorus coming into the process or leaving the process. So for example, we'll talk in detail in just a minute about what an installation looks like, but think of it like cruise control. In fact, you can probably think of all of these modules like cruise control. The phosphorus module specifically, the set point, in cruise control, you'd be using a set point of speed, right? Velocity, miles per hour, or kilometers per hour for our friends in Canada that I see have joined. What we're doing here with phosphorus is saying, tell me exactly how much phosphorus, orthophosphate, you want leaving the process. That's the set point. And then this RTC real-time controller measures the phosphate, measures the flow, and in every minute adjusts the ferric chloride, the alum, the polyaluminum chloride, pick your precipitant, whatever precipitant it is you're using, it adjusts that dose every minute in order to meet the actual demand to hit that target set point. So some of the benefits there. It can reduce chemical costs. We'll show you a couple of case studies here in the subsequent slides where significant chemical costs have been achieved, up to 55%. Reduces sludge production as well. Of course, when we're talking about chemical phosphorus removal, every gram of chemical, depending on the application, equals an extra gram of sludge. And so if we can reduce the amount of chemical we're dosing, we can also reduce the amount of sludge we're producing, and therefore the associated cost of treating and disposing of that sludge. And the last bullet there is ensuring compliance and providing peace of mind. It may sound like a strange bullet point there, but in some cases, smaller facilities with not a lot of manpower, not a lot of operators, maybe this is the biggest benefit for them, where they can set the chemical control system so that it's always outputting 0.6 milligrams per liter orthophosphate, for example. And when they come back on Monday morning, guess what? It's still at 0.6. So every plant, of course, has a little bit different needs, and these are just a few bullets which highlight those different benefits. So what does it do? What does it look like? Well, the chemical removal phosphorus controller starts with an orthophosphate analyzer and a sample preparation system. We use the Phosphax analyzer, that's a Hach product, and the Filtrax, which is a 0.15 micron filtration system that can be immersed directly into the system, into the basin, into the tank, into the channel, wherever you want to pull a sample from. It filters the sample and delivers it to the instrument. They're designed to work together. That's connected to an SC1000. The SC1000 is our transmitter, our controller, depending on your language. This is the interface for the Phosphax analyzer where you can set your output signals, you can make manipulations to the settings of the instrument, change display, things like that, and different communication capabilities such as Modbus, Profibus, wireless, Ethernet, etc. And the third component is the actual RTC, or real-time controller. And this is a device which basically, for those of you in the control world, is a mini PLC. But contained in that mini PLC are input cards, so we can pull, say, a flow measurement from the existing PLC, and an output card, which has a 4-to-20 or Modbus output for actually the dose of chemical in real time. Also inside of that is the actual algorithms where we're performing the math and every minute updating the output. Typically that RTC unit gets installed in a PLC cabinet. That way when we're pulling signals out of the existing PLC and putting them back into the PLC, very simple, right? We can just use the existing wires, inputs and output cards. It doesn't always have to be plugged into a PLC though. For this particular module, we can, if the chemical feed pump, say, can accept a 4-to-20 milliamp signal, we can send that directly to the pump. It doesn't have to go back into a PLC. Those three components are what we supply. What we also need is we need a flow measurement. Whether it's influence to the plant or plant effluent flow, we need a flow signal because, of course, we're talking about phosphorus loading. We're not talking about just concentration. And then the output from that RTC goes either back into the PLC to control a dose pump or directly to the pump itself. The pump that, of course, is adding our ferric, our alum, polyaluminum chloride, etc. And last, but certainly not least, are services. With this real-time controller and the SC1000, we have the ability to access and view this system remotely. So the benefit there is our tech support people can dial in once a week, check on the system, make sure everything's functioning correctly, make any changes that may be necessary, of course, with end user permission and the client's permission, and also put together and compile the data and issue a report if that's what the end user desires. That ongoing service is included in the RTC package. The nice thing here is it's one point of contact. For example, if we were to build one of these systems from scratch, I like to use the analogy that if I want to build a thermostat to control my air conditioning in my house because, gosh, it gets really hot here in the summertime. And I could go down to Radio Shack and I could buy components and circuit boards and everything I need to build my own thermostat. Or I could just go down to Home Depot or Lowe's or Ace Hardware and buy a thermostat off the shelf, right? The difference there, though, when you think about that analogy is that if I build a thermostat from scratch, if something goes wrong with it, who am I going to call? I have to go and troubleshoot it. And what if I'm out of town and my wife calls and says, hey, the thermostat you built, it's not working. Well, I'm out of town. I can't help. Same thing, when we build systems from scratch, who do we need to support them? We need to have an integrator perhaps on site or call them in. What's their response time? Maybe everything in the integration side is working properly. Maybe it's the instrument. So now we've got to call the instrumentation vendor. Well, maybe that was working fine. Maybe it has something to do with the algorithm, and the controls engineer has to get involved. So from an end user or client perspective, building from scratch may sound simpler and maybe be a little bit more cost-effective, but at the same time, who's going to support it? The nice benefit here is you dial Hach and we will support this. Meaning if it's an instrument problem, if it's an algorithm issue, if it's communications problem, an integration problem, we are the person or the organization who takes care of that. So just to highlight some of those things, and now let's move on to some more details. Installation options for the Phosphorus controller. There's two different ways we can use this Phosphorus controller. The first and the most common is in a feedback control loop. So for those of you maybe not aware, feedback control or closed loop control means we're measuring the process after we've performed the process. So as you can see in this diagram, we're measuring the phosphate concentration after we've added the chemical. So in this particular example, the nice benefit is if we make a set point of 0.6 milligrams per liter orthophosphate, we're measuring the result of that process. So you can see through the analyzer if it's at 0.6 or if it's not at 0.6, and then feed back upstream to control that process and add more chemical or add less chemical. It also has the least amount of process risk. Process risk being, of course, in a feedback loop system like this, there's very little risk that you'll be out of compliance. If your compliance value is 1 milligram per liter total phosphorus and you're always running a 0.6, this system will make sure you're staying at 0.6. Low risk. However, not every process can be automated in that manner. And sometimes we have to do feed-forward or open-loop control. The difference here is open-loop control is based on measuring before we add the chemical or before we actually perform the process. That requires some sort of predictive model be installed in the controller. All of that is included in the RTC module. It's already there. It's just a matter of which one are we going to use. So when it shows up on site and it's installed, it's just a matter of we're picking either the feed-forward or the feedback. There's no special software that needs to be shipped in and downloaded or anything like that. The benefit for the feed-forward system is that if there are plants with large influent phosphorus swings, sometimes it's better to measure that swing before you add the chemical, because maybe the chemical dose point, we can't get close to that. Maybe we're measuring with the analyzer 2 to 4 hours detention time downstream. Well, that's no good. That's not a good control system. So in that case, a feed-forward or an open-loop system where we measure before the dose would be more effective. However, there is a little higher level of risk. We don't know exactly how much phosphate or total phosphorus is leaving the plant. All we can do is estimate that or put another instrument on the end of the plant, maybe run some grab samples, maybe a composite sampler, but with straight open loop or straight feed-forward control, it is just that. We're measuring before we perform the action. And so we do not know exactly how much is leaving like we would with closed loop. So this may look very simple, and indeed it is from an installation and an integration perspective. The benefit being, of course, it's literally off the shelf. For the phosphorus module, we've had these in Europe and been selling them in Europe for about 4 years now, I should say, all of these modules. And just recently, in the last year and a half, started bringing them over to North America. Total installations of the phosphorus module right now between Europe and North America is about 130 units. And so what I want to emphasize here is 130 installations between Europe and North America. This is, quote, new to the North American market, but it's certainly not new from a product perspective. Very much tested. The algorithms are proven. The manuals are written. The support is simple and understood. So just want to give that perspective that there are 130 installations of this particular phosphorus controller between Europe and North America. One of the installations here in the United States is in Beaver Dam, Wisconsin. And for those of you who have access to WebTech proceedings that were online last year, or maybe your company or your plant has access to the proceedings, there was a paper we presented on Beaver Dam and this exact data in more detail. We are more than happy to send you copies of similar papers that don't violate any copyright infringement. But if you do want to read the direct paper that was submitted and presented to WEF, you can do that on the proceedings page. What we're looking at here at Beaver Dam is about a 4.7 million gallons per day plant. And they have a few different food manufacturers in town. So their influent phosphorus is right around 25 milligram per liter dissolved orthophosphate. And just to give you a perspective on that, most wastewater plants are 7 to 8 milligrams per liter total phosphorus. This was just dissolved orthophosphate. So we're not counting any particulate phosphate, we're not counting any organic, any polys, etc. That was just through a few grab samples we ran on site. And what we're looking at here are the two graphs. You can see that 0.6 milligram per liter set point. And then the darker blue line is the actual phosphate concentration around that set point. The graph below that shows the ferric chloride dose in real time. When we first were invited to come install this and work with the operators at Beaver Dam, they were feeding a static 12.5 gallons per hour of ferric chloride. Regardless of influent conditions, regardless of flow, 12.5 gallons per hour was the simplest and most effective way for them to operate without better tools. Once we had the phosphorus controller installed and they had these better tools, we were able to vary the dose in real time to make sure they maintained that 0.6 milligram per liter orthophosphate effluent set point. And for those of you control engineers in the audience, integrators, you can see there's a little oscillation around that set point. We can certainly do better, and we are doing better at this particular installation, making it less of an oscillation. But you know what? We're not going to show you all just good data. We want to show you some of the data that we learned from as well. So that's what we're looking at here. At Beaver Dam, this particular site was 56% reduction in ferric chloride. So based on the 12.5 gallons per hour they were feeding to the real-time controller's dose, the difference was 56%. In essence, when we did the math on that, on the installed cost of the phosphorus control system, the return on investment was 6.8 months. I thought about rounding that to 7 months, but 6.8 just seemed to have a better ring to it. So at Beaver Dam, they paid for the installed cost of this system in 6.8 months. And again, 4.7 MGD plant with some pretty heavy, of course, influent phosphate numbers. We recognize every plant is going to be different. Every return on investment is going to be different. It may not be a fit at all locations. But we're certainly more than happy to evaluate that with you. We do have a team of individuals that can help evaluate your system and see if it's going to be a fit or not. So that's Beaver Dam, and again, we have these papers. If you'd like a copy, we can certainly get those to you, or if you have access to the WestTech proceedings, feel free to download it from WestTech. Moving on. The next module I want to talk about is the Nitrification Control System, what we call the RTC 103. So we're shifting gears here. We've gone from phosphorus control to nitrification control now. And this particular module is designed for continuous flow plants. Think traditional activated sludge, aeration basin, clarifier. This is not designed for sequencing batch reactors or oxidation ditches. We'll talk about one in a few moments that is designed for that. So it's designed for continuous aeration. The concept here is we're controlling aeration based on ammonia load in real time. The difference, of course, being most plants today control aeration based on a dissolved oxygen set point. So maybe operator looks at the data from yesterday, looks at what may be happening later this week, maybe historical data, and says, today I want a DO of 2.5, and they type 2.5 into the SCADA. Well, this module is very similar in the fact, though, it's looking at the real-time ammonia coming into the aeration basin, and using a feed-forward model, it calculates the dissolved oxygen set point required to oxidize, to reduce that ammonia. I guess that's a really bad choice of words. It is oxidize, but remove the ammonia, not reduce, to a certain set point that is also programmed into the SC1000. It changes that DO set point every 15 minutes. So the idea here is a lot like having an operator making these calculations every 15 minutes using an ammonia measurement on the influent to the aeration tanks and one on the effluent of the aeration tanks, making sure they're maintaining or below that set point that's programmed. I mentioned that we've had these in Europe for several years now. There are 41 N modules, nitrification control systems, installed in Europe. There are 2 that we are currently installing here in the United States, and of course more that are coming soon. Those are the only 2 I can speak of at this time. What we've seen in Europe is for those plants that are already performing DO control with a DO probe and a good aeration control system, maybe cascade loops, we're seeing when you add the nitrification control system, the energy costs drop by 10 to 30%. So even though maybe we've saved 20, 30% energy cost by switching from static airflow control to DO control, switching to nitrification control can save between 10 and 30% more. So of course, there are caveats there. Perhaps some facilities, the blowers are so oversized that even if the controller asks for a DO of 1.5, you can't go below 2. The blowers are just too large. Well, that would certainly limit the energy savings. And then there's the other side of the equation. Maybe the blowers aren't large enough. Maybe the system's at capacity, and there's just not enough nitrification capacity. So we certainly recognize it's not a fit for everyone. And like the phosphorus module, we're more than happy to evaluate that and help you make your decision if it is a fit or isn't a fit. So similar to the phosphorus controller, the components here for the nitrification controller begin with some sort of ammonia measurement. In this case, we're talking about the Amtax ammonia analyzer. Now, if I press the pause button here for just a second and opine, if you'll allow me, on the difference between, say, analyzers and probes when it comes to ammonia, if you've seen us or went to our workshop at WestTech on instrumentation for nutrient removal, there are sensors on the market today which are ion selective for, say, ammonia or nitrate. However, those sensors today are similar to DO probes 12, 15 years ago. Membrane-style sensors that need to be cleaned, need to be calibrated, need to have the membranes replaced, et cetera, et cetera. They're higher maintenance than the analyzers. So for me, as a controls person, if I'm going to want a good field sensor, if I want something measuring ammonia and I want it to be reliable, I don't have to worry if it was calibrated correctly. I don't have to worry if it was cleaned properly this week. The analyzer makes more sense because analyzers clean themselves, they calibrate themselves, and measure lower, they measure more accurately. So from a controls perspective, it's win-win. There may be a little higher capital cost up front, but when you look at the return on investment or a 7-year cost of ownership, they're pretty much a wash. So I will get off my soapbox between analyzers and ion selective electrodes. There are certainly places for ISEs. I enjoy using them for trending, but when we're talking about control, we want better measurements. So likewise, with the MTACs, we have the Filtrax filtration system that pulls a sample and delivers it to the instrument, and those two are integrated to work together. With this particular control system, we also pull in suspended solids. Therefore, we have a suspended solid sensor listed as a bullet, the Solitax. And we do have the option of pulling in dissolved oxygen measurements and temperature as well. Not necessary. We'll show you why in just a minute. Connecting to the SC1000, and again, that's where we interface with everything, with the instruments, with the real-time controller. All the programming, all the set point and data that needs to be entered is done through the touch screen of that SC1000. So for those of you who are familiar with RS Logics and the different ladder logic programmings and function block diagrams, you don't have to know those in order to program the real-time controller. The real-time controller is completely programmed through the touch screen on the SC1000. So anybody with a pointer finger can do it. Also, the real-time controller there, just like with the Phosphorus module, those are the components that are supplied off the shelf. Like the Phosphorus controller, we're pulling in a flow measurement, so we understand the load of ammonia coming into our aeration tanks. And we output from the controller a dissolved oxygen set point. That set point is then fed back into the PLC, and that set point is then integrated into the PLC. So there's the differential and a little bit of a line that I want to draw. We're not directly controlling airflow. We're not directly controlling header pressure. We're not directly controlling valve percentage if we're doing most open valve, things like that. All we're outputting is a DO set point. And your existing DO control system accepts that set point and then implements it. One of the key pieces we've recognized is that good DO control systems are elegant, and they really do require good engineering and good integration. It's very difficult to have an off-the-shelf DO controller that's effective at a majority of the plants around the country. So in that case, that's where we drew the line. We will output a DO set point and let the existing aeration control system implement that set point. However, that being said, we do also have the ability through a 4 to 20 milliamp output to control a blower, to control surface aeration for those plants that don't have a good DO control system already. So that is an option. It is definitely not something that we're pushing because obviously good DO is going to require a good DO controller behind it. And the services. Likewise, we're talking about here the remote service where we can dial in and look at the system, make sure everything's working correctly, look at the preventive diagnostics and the instrumentation, and make any changes that the end user would like for us to make. Just like with the Phosphorus controller, recommended locations or recommended installation. Typically, we start by measuring ammonia coming into the aeration basin and ammonia leaving the aeration basin. So again, we need to know the load coming in, and then we're going to compare that to the effluent number, which is comparing to your set point. So through that SC1000, end user maybe says, hey, I want 1 milligram per liter or less of ammonia leaving my aeration tanks at all times. The influence side measures the load, uses a feed-forward controller based on the activated sludge model for nitrification, a little bit more than that, but that's the base of it, and says your DO should be 2.5. Well, the downstream ammonia sensor acts as a feedback control loop. And based on the aeration tank size and the flow, it says, okay, 4 hours ago I suggested a DO of 2.5. How much ammonia is leaving right now? Oh, it's 1.0. Perfect. Don't make any change. But if it says, gosh, it's 0.5 or 0.2 ammonia leaving, hey, let's trim that feed-forward model and calibrate it to the process better. So we have, in tandem here, a feed-forward control system and a feedback working together. Suspended solids and, of course, DO that we talked about as an option can also be fed into that 1,000. Highly recommend suspended solids be used with this system. So therefore, we do know the true mixed liquor suspended solids concentration in real time, and that helps us understand better the nitrification capacity of the system. All those sensors are connected to the 1000, which is connected to the real-time controller, the N module, nitrification module, which is installed in a PLC cabinet for easy integration. And of course, that communicates back and forth with the PLC and the flow meter, and that's what our typical simplified installation diagram would look like. Now, of course, you're looking at this diagram and you're saying, that's not my plant in Perrysburg. My plant does not look like that at all. And we recognize every plant is different. So with this simplified diagram, we certainly want to say that your plant may be a little different. Where you need to put ammonia sensors may be different than, say, Grand Rapids, Michigan, may be different than Greeley, Colorado. Identifying those locations is our task, and that is part of the services and consulting, quote, if you will, that we offer. Some case studies, in particular here, we're going to highlight 2 out of the UK. As I mentioned earlier, there are 41 installations of this module in Europe, and we are currently installing 2 in the United States. The first is in Bournemouth. When we look at these numbers, what I want to highlight is 30% less aeration energy is on top of good DO control. So, for example, they already had a good DO control system, and they were already controlling to a specific DO set point. But what they found was maybe at a DO of 2.5, the ammonia was dropping to 0 halfway through the aeration basin. So the other half of the aeration basin wasn't doing any nitrification. It was just wasting air, frankly, keeping things mixing. And so in this case, by controlling based on the actual ammonia load, they were able to save an additional 30%, which, as you can see here, Great Britain pounds, GBP, was 80,000 a year. At the time this was written, I believe the conversion was about $1.60 per pound. So just to give you some U.S. dollars to Great Britain pound conversions. Likewise, Southampton in the UK, they were 20% less energy, and in their case, savings was much higher because they're a much larger facility. What we're looking at there in the graph is the blue line was the RTC-controlled train, one of them, and the red line was a manually controlled train, an operator-controlled train. So this was a fun data set to work with because we're looking at an experimental train and a control train. So this is almost like real science here. You can see the blue line, there's significantly less aeration, less airflow than there was with the red manually controlled train. Now, I'm sure there's more than one of you who are looking at the green line and say, wait a minute, Bob, all the way on the right, that green line drops to 0. There's a point where the operator-controlled and the RTC-controlled met, and they both fed the same amount of air. Yes, you're absolutely right. Keen observation. Good job. It's very difficult to make WebExes and podcasts interactive, so that's one way of doing it, I suppose. Here is that data, a little bit closer, a little bit more fine. This is effluent ammonia with the blue and the red, and the gray line is the influent ammonia load. And what we see here is under the standard control system, the effluent ammonia, this was operator controlled, effluent ammonia crept up to about 13 milligrams per liter. You can see the big gray spike behind it as the influent load peaked. whereas the real-time controller limited at about 5 milligram per liter ammonia leaving the system. So even though they both use similar amounts of air, the amount of ammonia leaving the process was greatly reduced with the real-time controller. As you can kind of see in this data set, their target for ammonia leaving the aeration tanks was 2 milligrams per liter. And so most of the time we remained under that 2 milligram per liter set point, and only with this large slug did it go over 2 milligrams with the real-time controller. And when it did, it was very short and then immediately came back down. So those are some case studies and data out of Europe for the nitrification controller. Last but not least, I want to move on to the final topic for today, the nitrification and denitrification control system. So this system is designed for, as we would say, intermittent aeration processes. What do you mean by that? Well, plants that perform nitrification and maybe denitrification in the same tank. So an oxidation ditch that might perform on-off aeration. Sequencing batch reactors that may perform both nitrification and denitrification in the same tank. Schreiber-type systems, which may perform nitrification, denitrification in the same tank. So those types of processes. What we've seen, again, in Europe, we've had 62 installations of this module, and we have a few lined up here in the United States, but again, nothing I can really speak to yet. We're seeing energy cost savings of 10 to 25% at those oxidation ditches and sequencing batch reactors. And again, that's on top of DO control, okay? So I want to focus on that this is not just going from no control to perfect nitrification, denitrification control. This is going from good DO control to enhanced process control based on actual water quality. The pieces and components, just like with the previous two, we start off with sensors, whether that be the Amtax for ammonia, the Filtrax sample delivery system, the Nitritax for nitrate, DO sensors, etc. Integrated into that SC1000, which is also communicating with the RTC. And like the other modules, all the programming and all the set points are entered in the SC1000 touchscreen. We're bringing in a flow measurement, so we understand the load coming into the process. And simply outputting back to the PLC or maybe directly to the aeration system, depends on the plant. Either the air is on or the air is off. So if you think about it, what we're doing here is using ammonia and nitrate targets that are entered into that SC1000. And if you think about an oxidation ditch with 2 brush aerators, maybe when it says, okay, turn on the air, we need to nitrify. My ammonia is too far away from my target. It'll aerate and nitrify until the ammonia is brought down beneath the target value, and then it'll look at the nitrate and say, nitrate also is above my target value. Let's turn the air off. So one of those brush aerators will turn off. And again, as long as there's sufficient mixing. And denitrify until the nitrate set point is reached. And the nice thing about this particular unit is there are not just targets or set points that get entered, but also weight that can be adjusted. So perhaps we want to provide, maybe we're in California and we're dealing with Title 22 reuse water, and we need to be below 10 milligrams per liter total nitrogen. Maybe we've never had a problem nitrifying, but gosh, denitrification is challenging with my plant, with my ditch. So we could add a greater weight to the nitrate target, and therefore it may spend more time denitrifying than it will nitrifying, because it recognizes the nitrification capacity is faster and better at that particular process. So there are different things that are available here to be, the best word I could think of is tweaked or adjusted to make it better fit for an individual process. There is an optional DO controller, and again, this is not an elegant, compound cascade loop system. This is simply a 4-to-20 or a relay that is asking for different aeration intensities, perhaps, or a 4-to-20 asking for a 0 to 100% aeration control. Again, designed for plants that may not have a good DO control system. And last but not least, services. Taking care of this remotely, having our tech support people have a window into it so they can view what's happening, make any changes to the instruments, perform any required maintenance remotely, and things like that. Along with those services, and I failed to mention this previously, we will have actual service personnel in North America come on site maybe quarterly, maybe every 6 months, depends on what the particular instrument needs, and perform preventative maintenance as well. For example, the Filtrax is a quarterly preventative maintenance where we'll come change pump tubing, take care of the membrane filters, evaluate the system, etc. And our techs will actually come on site preventatively and do that. That's also part of that service package. And it's true for the N module and the phosphorus controller. Here is a case study out of Europe. Again, 62 installations in Europe, working on 2 here in the U.S. This is an industrial facility. So for those of you on the phone who work for various industrial firms, this might be of interest to you, specific industrial application. There's a leather production facility, a tannery. And if any of you have ever been to a tannery or understand the chemicals that go into tanning leather, you'll recognize that wastewater treatment at a tannery can be both an art and a science. It's very difficult. This particular plant had an oxidation ditch that was trying to meet total nitrogen limits and get less energy consumption. Here were their target values. They wanted to keep the ammonia less than 5 milligrams per liter and the nitrate less than 20. So what we're looking at here at this chart is on the left axis, we're looking at ammonia concentration, oxygen concentration. On the right, we're looking at nitrate concentration. So the green line, as we watch that green line cascade from the left to the right, is nitrate. And the red line is ammonia. You can see then the bottom red and blue lines are when the controller is asking for aeration on or when aeration is off. So 0 or 1, you can think of it in that manner. And you can watch slowly as the nitrate concentration drops down to the 20 milligram per liter target value, and the ammonia concentration drops down to about 5 milligram per liter, the target value. Over the course of this particular installation, the energy savings were about 25%. So again, that's just simply controlling a brush aerator. It's saving 25% on energy costs. The total nitrogen, however, was reduced by 90%. And you can see that just illustrated there in the simple graphic. But when it was measured before the installation, you can see nitrate was between 140 to 160 milligrams per liter, and then eventually brought down to the appropriate set point of about 20 milligrams per liter. So pretty significant here, especially in I love industrial wastewater because it takes municipal wastewater and multiplies it by 100. It makes everything higher, more concentrated, and generally a little bit more challenging to work with. Not always, but generally. So to summarize, and then we'll have time for questions. I see there are several, and I appreciate that. Please, if you have questions, type them in. I do want to get to those questions, as many as possible, and if not, I'll call you or email you with replies. First and foremost, we talked about chemical phosphorus removal. Benefit there, reducing the precipitant use, the ferric chloride, the alum, the polyaluminum chloride, and reducing sludge production. To date, about 130 installations of this particular module between Europe and North America. Secondly, we talked about the nitrification controller. And this was basically ammonia-based aeration control, reducing aeration energy and better control of influence bites. whether they come from the collection system or whether they come from centrates and our wet wells that suddenly kick on and dump into the influent. And the third module we spoke about was the nitrification and denitrification controller. Again, the concept there was to reduce aeration energy and total nitrogen. There are 62 of those installed so far, and 41 of the nitrification controllers. And that's the concept we're talking about, these off-the-shelf real-time controllers. There are more modules in the pipeline, if you will, that if you keep your eyes peeled on Hach.com, you'll see more and more of them be launched here as we roll these different modules out for different applications. And these are the three we're focusing on today. Appreciate your time and attention. Hopefully I've been able to keep your attention. I know that can be a challenge. And at this time, I'm going to look at the questions. And just to verify, I believe we have 15 minutes. Is that correct for questions?
That's correct.
Thank you. So let's answer some questions. Holy moly. Thank you for submitting questions. And if you still have more questions to add, please do so. We will get to them. First question, you mentioned the Wisconsin plant, Beaver Dam, was up and running in a day. Is that standard? Yes, that is standard. The Beaver Dam location, so we shipped everything on site, had everything installed, literally the analyzer installed in a day. The RTC was in the PLC cabinet. The integrator was on site and pulling 4-20s and landing 4-20s. Everything was up and communicating in a day and turned on, controlling their ferric chloride dose in real time. So funny thing about Beaver Dam, and Rob at Beaver Dam won't mind me sharing this with you. We had everything installed and running the first day. Everything looked fantastic. The real-time controller said, don't dose a drop of ferric chloride. You know, the set point was 0.6, and they were constantly about a 0.3, 0.4. So the real-time controller said, no ferric. So we operated that way for about 3 or 4 days where it just didn't ask for any ferric chloride because we were way below the set point. And then suddenly it would slowly creep up. The real-time controller kicked on, started asking for ferric chloride, and asked for more and wasn't getting what it needed. Turns out whoever had last painted the pipes in the pipe gallery painted the valves, the ball valves, the same color as the pipe. So we missed one of the ball valves, and it was actually still closed, not adding any ferric even though the pumps were on and trying to dose ferric, the valve was closed. So we all make silly mistakes. That was the one we made there at Beaver Dam. Once we opened up that ball valve, we were back in control and back under compliance, no problem at all. So maybe there's a lesson there. You know, maybe paint the ball valves a different color than the pipe. Just saying. Let's see here. You indicate phosphorus control is based on residual phosphorus leaving the system. Any controls or any success on controls based on MLSS and influent BOD, COD, or TOC? This is from Dirk. Dirk, good question. So his question here is based on your mixed liquor suspended solid, your influent organic concentration, the type of process you have, if it's a BioP process or if it's just a traditional activated sludge. You know, we can work and estimate what some of the phosphorus removal capability of the biological process is. We do have that kind of built in, Dirk, to the phosphorus controller. In other words, if we're using the feed-forward controller and the plant is the biological phosphorus removal plant, so an anaerobic and oxic environment for BioP, we do have the ability to type in the basic BioP percentage. How much of the influent phosphate will be removed biologically? How much does the chemical need to polish or dose to reduce down to a certain set point? So it's kind of built in there, but this module is specific to chemical phosphorus removal. And in that vein, we kind of ignore, we don't want to know the biological aspect. I would rather, if it's a biological phosphorus removal plant, and maybe we're adding ferric or alum at the end of the mixed liquor before it goes to a secondary clarifier, I would like to measure the phosphate either downstream of that dose point ever so slightly where it's well mixed and representative, or after the clarifiers. I wouldn't want to measure before the biological phosphorus process, because if something were to hiccup in the biological process and we didn't know that, then we may see there's 8 milligrams coming in, the BioP hiccups, there's 5 milligrams perhaps going through the clarifiers, and we're only dosing for 1. I would rather use a feedback controller, measure what's actually happening, or if we do choose to go feed forward, measure right before the dose point, right at the end of the mixed liquor. I wouldn't want to measure before the mixed liquor. I hope that answers your question. Looking at other questions here. Let's see here. So, does Hach have FDT group approved DTM for the SV1000? If not, when will it be available? I see your question there. Thank you. By the way, Manchester, Connecticut, shout out. I grew up in Hebron, Connecticut, which is just down the street, so power to the New Englanders. I do miss lobster. I live in Colorado, and I miss good lobster. Just can't find it here. To answer your question, yes, we do have FDT group certification. This is in regards to Profibus communication, for those of you who may not be familiar. And FDT group is an organization that basically certifies or approves certain parameters and information that can be accessed from the sensor through Profibus. So, sorry for those of you who speak Profibus fluently. I'm trying to make that very simple. But in essence, yes, we did receive FDT group certification for the 200 and the 1000 last year. So if you need more information on that, please feel free to give us a call, and we can get that information into your hands. Another question here. Aha! You show dosing phosphorus after the aeration basin. Is that the normal practice? We have always dosed aeration with phosphorus before the aeration basin. So Paul, I thank you for that question. Now, I'm looking at your question and realizing you're asking about dosing phosphorus as opposed to dosing phosphorus removal. And so I want to perhaps throw a caveat here. The phosphorus controller is designed for removing phosphorus chemically. So if this is an industrial process and maybe your BOD to nitrogen to phosphorus ratio is not correct, so you're adding phosphorus in the form of maybe phosphoric acid or something along those lines, that is not what this controller is designed for. It's not designed to add a phosphorus chemical. We can do that. We just don't do it with this real-time controller. We do it with the existing SV1000. So you're correct. If it's an industrial process and you don't have enough phosphorus present for the biology, yeah, you'll have to add phosphorus before the aeration basin to keep the biomass happy. What we're talking about is we're talking about adding some type of precipitant or chemical that will remove phosphorus. And likewise, if you look through WEF's different manuals, there's the biological nutrient removal operation, automation of wastewater treatment plants. There's a couple different manuals out there, manuals of practice, that talk about the best places for dosing ferric chloride or alum to remove phosphorus. And one of the things we noticed through all of this is if you add too much ferric chloride before the aeration basin, then the biology who needs phosphorus may not get enough and cause them to be stressed. And when they are stressed, they can do all kinds of things, a polysaccharide slime bulking. They could have settleability issues. And so for plants that we talk to that maybe are dosing ferric or alum at the beginning of the aeration basins, we really want to sit and have the conversation of what would it take to move that dose point to the end of the aeration basins. We can settle out the phosphorus and the ferric and the alum and the clarifier and not stress out the biology as much. Again, those are sometimes bigger, broader conversations that need to happen with your consulting engineer, but more than happy to help facilitate that. You guys have some fantastic questions here, and some of them I think would require more than 5 minutes of a response, so I'm trying to pick the ones that may be the easiest, not necessarily easiest, but be able to answer within 5 minutes. Here's a question from Leslie. I don't have much experience with denitrification, but it seems that denit control could be more complicated due to the need for external carbon, or maybe carbon dosing remains relatively consistent. So indeed, when we talk about the denitrification controller, we're talking about systems that already have enough carbon in the raw influence in order to perform denitrification. We're not talking about a system which is going to be adding carbon, not yet. I did mention there are other modules that we're working on, and I won't say specifically what we may be working on, but may have something to do with external carbon dosing for denitrification. So, not without saying anything specific though, but if I were just dreaming, that might be one we would be working on. Same question, although a little different. How about suspended solids? Any type of real-time controller for solids control? Yes, we are working on that, but I'll say the answer is not yet. One that I can tell you we're about to launch, so Liz, don't hate me for this, but is a sludge thickening module where we're going to be helping control polymer dose and dissolved air flotation thickeners, drum thickeners, gravity belt thickeners, things like that. So measuring the influent solids load in real time so you can match your polymer dose in real time. Also with a feedback system of suspended solids and the filtrate, for example. That one is not fully launched yet. You will see it, however, in the next 30 to 40 days. So I feel comfortable that I shouldn't get into too much trouble talking about it right now. And 3 minutes left. Simple question here, it looks like, from Chris. What is the MDL of the sensor? I assume, Chris, you're meaning the MDL of the MDL is method detection limit. What is the lowest the sensor can measure? Every sensor, we've talked about several today, has its own detection limit. I'll just rattle off a few of them because I don't know specifically what sensor it is you're speaking of. But, for example, the phosphate system, the PhosStax analyzer measures down to 0.05 milligrams per liter orthophosphate. Of course, at that level, the accuracy is plus or minus 0.05. So really, from an application perspective, if we're going to be below 0.15, we would want a different system. We do have another phosphate analyzer called the Series 5000 that can measure down to 0.004 milligrams per liter, or 4 micrograms per liter. And the accuracy is plus or minus 4 micrograms. So we do have a system that can measure in the ultra-low phosphorus range. And again, we're talking about dissolved orthophosphate, to be specific there. Some of the other sensors we spoke of today, ammonia, the AmTax, measures down to 0.05 milligrams per liter. Again, accuracy plus or minus 0.05. In North America, that doesn't seem to be a big concern as much as with phosphorus, which there are some phosphorus limits here in the States at 0.05 total phosphorus. So have to keep those in perspective. What other sensors did we talk about? We talked about nitrates. On nitrate sensors, detection limit on the Nitritax is 0.05 milligrams per liter. Nitrate as nitrogen, so NO3-N. Same thing, ammonia is as nitrogen, phosphate is as phosphorus. Accuracy of the Nitritax is also plus or minus 0.05. So, really if we want to measure accurately below 0.15 with the Nitritax, we may want to go with a different solution there. Most plants in the country, though, are looking to maintain, a 5 to 10 milligram nitrate set point for that NDN module. So the Nitritax is typically a good fit there. Those are the sensors we mainly talked about that would require MDLs or detection limits. So, Chris, I hope that answers your question. If not, if I didn't answer your question fully, or if you've got more questions, please feel free to type those in there. We will get back to you on those questions. I do sincerely appreciate you attending today. I hope I didn't make you fall asleep, or if I did, I hope it was well needed. I hope you really needed that rest. If you have questions, you want to follow up with us, our contact information is there on the slide. Please feel free to email, call at your convenience, and we'd be happy to help answer questions you have or determine if a certain system is a fit for you.
Well, thank you very much, Bob. That was a very informative presentation, and I realize we do have quite a few questions here that have not been answered, but I'm sure you'll check them out and respond as you can to the email addresses for the folks who asked the questions. As a reminder to attendees, this presentation will be archived within 24 hours and can be accessed from the homepage at waterworld.com. A reminder email will be sent to registrants complete with a direct link to the archive. We want to thank you for joining us today, and Bob, thanks again for the great presentation on off-the-shelf real-time control. Thanks.
My pleasure.